Let's continue with our afternoon session. And the talk, it's my great pleasure and honor to introduce our last speaker of this afternoon session, Professor Yuri Tschinkel, and from Hamilton Foundation. And today we'll talk about equivariant geometry. So please.
Well, thank you. Thank you very much. It's always a great pleasure to be here. So I'll be most talking about algebraic varieties over fields, characteristic 0. And most of the time, the ground field is algebraically closed. And I consider actions of finite groups, so such varieties. So X most projective, action is regular, generically free. And well, when we think about these questions, there is sort of a passage that keep in mind, namely, you can start from varieties as G actions, then you can look at the quotient stack, and then you can look at the invariants. And at each step, there is a loss of information. So in particular, of course, we can imagine there are many double covers of P2, different varieties, at P3 different evolution, complex surface of evolution, take the quotient to get P2, of course, the original actions are completely different. So today I will focus on that middle part, applications of these kind of stacks to problems both in the invariance theory, which is the right side, the field of invariance, and also in the study of G actions up to birationality. Okay, so let me remind you, variety is rational if it's birational to projective space, stably rational if it's rational after you multiply this projective space, and unirational if there is a dominant map from projective space to the variety. And of course, we don't really understand the plot of the rational variety. And that's a good talk. Let's have different notions, dimensional slide curves, so theorizing things like this. Maybe all rational projective parameters are irrational. Maybe hypotheticals of certain degrees, always be hypotheticals, always be irrational, and things like this. But in any event, it's just a classical problem to try to distinguish these notions. And indeed, distinguishing rational and stably rational varieties became possible, and particularly unirational and non-rational varieties, thanks to fantastic work Clemens Griffiths using intermediate Jacobians, cubic threefolds, Mani Noskovsky, certain quartic threefolds are unirational, but not rational. And then Art and Mumford examples, you look at conic bundles over P2. If the discriminant is not too large, they're unirational, but they produced in these ranges non-rational varieties using the Brauer group. So this was sort of in the early 70s. But of course, there are examples of unirational varieties, a priori unirational, where you don't have to do any complicated geometric constructions. You take a finite group, and you take a portion of representation of a finite group by the group. So it's dominated by a finite space, it's obviously irrational. Now, is it rational? So, well, it turns out that if the group is abelian and the ground field contains enough root security, it takes the exponent of the group, but if all the root security are in there, then the quotient is rational. This question of rationality of quotients of representations goes back to the problem. It goes back to Hilbert actually, who showed that if the quotient is rational, then you can solve the inverse Galois problem over the field that you're working over for the group that you're looking at. And so that's why it was sort of an important question, it was an important conjecture. Well, is it true that for any finite group you take a representation when it's rational? Now, when you look at these simple constructions, representation modulo group, the first thing that you see is that the variety is really singular. At the origin, you have the whole group as a stabilizer. And well, of course, look at the issues, it's like singularities. Of course, here you have different stabilizers for the subgroups of the groups, linear subspaces, and it's a pretty complicated singularity that you see. And well, this motivated to go away from, let's say, looking at smooth models, since you don't know, canonical smooth models for these things, to considerations of the function field rather than the variety. I mean, we're only interested in birational issues like rationality, and so we may as well work with the function field, and then you think about valuations, divisorial evaluations, about the absolute Galois group of your field, and so on. And the kind of invariance that people look at when they think about fields is Galois cohomology. Distortion coefficients that I omit here. And a key definition in this field is unramified cohomology. So there is actually a homomorphism, like a residue homomorphism, which goes from HI of the field to HI of the completion of the relation, HI minus 1. And well, you take the intersection of all the kernels of the divisorial evaluations, you get some subgroup, and that subgroup is an important invariant. And the basic properties are that, well, that group vanishes when the index is bigger than the dimension. It's actually a stable birational invariant. So therefore, it's something we say to look at. And then, of course, there's functoriality and all kinds of things. And then you want to understand, well, what can we say about two rational varieties in general? And the basic result is that for I equals 2 and 3, it's actually fine under the fact formula. And so, well, then you can ask, well, is it true that for all the rational varieties and all I, those groups are finite? That, of course, we don't know, but of all of those, the most important in applications turns out to be the Brauer group, the unramified Brauer group of the function field that turns out to be the honest Brauer group of a smooth projective model of the function field. And as I said in the examples we have in mind, you don't really want to work with smooth projective models. So that's the correct definition. And well, it turns out that it's accessible in some cases, in many cases, and I will show you how to compute these things. And so it became a standard tool in this field. So Saltman and Bogomolov produced first counterexamples to Noether's problem. They found groups G, where the field is not rational. In fact, it's not even stably rational. And the invariant that was deployed is that unramified Brauer group. So they computed, Bogomolov in particular, gave an algorithm how to compute the unramified Brauer group in terms of G only. The representation is irrelevant. And well, as always with good problems, well, you solve something particular, but then it opens the door to many other interesting things. And so the original computation by Bogomolov, in fact, triggered many developments in birational geometry, in particular in abelian geometry. We were trying to reconstruct a function field from the absolute Galois. So here is one of the surprising results, to me, at least in this area, inspired exactly by computations of these kind of abstractions, and Brauer group, and it says the following. So look at any algebraic derivative over a dimension at least 2, that's valid, that's important, curves, over the closable finite field. So the reason for this restriction is that, well, this is the field that's algebraically closed and has no non-trivial relation. So you don't need to separate the geometric relations from the relations that you get from ground. So pick any unidentified class. Then it turns out, and that's a series of universal spaces, that that class can use from a certain map from your variety into very simple varieties and the products of predictizations of vector spaces, which are representations by group G, which is abelian, acting projectively on each vector. So acting projectively means, well, you projectivize a representation of a central extension of G. Okay? And then on the projective space, you have an actual abelian group. So it's kind of unbelievable that, well, what does it mean, universal spaces? Always, you want to understand the family of varieties, curves, well, there's a model-like space, and it's just the map of the react. This is how we think about universal spaces. Any individual unidentified homology class is a thing from these model this universal space, model varieties. Okay. Yeah, so this is some theorems that we proved. Now, let's talk about no-closed ground fields. And again, we're interested in rational varieties. So let's consider geometrically rational varieties. We don't know that it's rational over ground field. Let's assume we have a rational form. Well, then you can look at universal torsions. It's a certain torsions under algebraic tori. So it's the known tori. Let's say the full field. Look at the characters. It's a portion 3 minus 3 model. Velocity, 3 models. All right. And well, we have torsions. And in this case, the universal torsions that refers to the form of dual to the level severity level on the right. Now, they play an important role in arithmetic, in questions concerning existence of rational points. Now, we have a rational point. We got to learn deploy it for abstraction, Hasse principle, but if you have a rational point, then what we call the weak approximation, things like this. So, in particular, over such ground field such as Q, we also mentioned Riemann abstractions, other purposes in geometry or other ground fields. And so one of the conjectures here is that, well, you start with your variety that's geometrically rational. You know examples where they're not rational of the ground field. You go to this torsor, and the conjecture is the torsor is rational over the ground field. Now, initially, it was formulated for Delpezzo surfaces, but since nobody could prove it for Delpezzo surfaces, I think Lyotelin decided to make the conjecture for everything. Well, that's what we have. And how should we think about it? As always, you need some evidence. Well, if you start with a toric variety or no-closed field, then the universal torsion for it, it's Fn space, and of course it's rational. And so we know that we read the conjecture is true. And then there's one particular example that's a difficult paper, the little from the kinetic and the dire. So a particular degree 4 Delpezzo surface, different bundle of the ground field, and the splitting S3. That's it. It seems so particular, and that's the only case that's been found so far. However, there is this beautiful result of collective such that, well, while they cannot prove that the torsion is a rational variety, at least they can check that some abstractions for rationality vanish, namely the anode vanishes. And more recently, somebody proved that the anode H3 from focal theory. So when you look at torsion of the Delpezzo surface. Okay. So the moral from all of this is that
these torsors untwist unrarified cohomology. So you had unrarified cohomology on the base, abstracting rationality, you pass to this torsor. This conjecture for torsion is rational, you don't know that, but at least the abstractions to rationality vanish. So that motivated Bogomolov and myself to look at splitting varieties. So consider a variety over a field K, and we will say that such a variety admits a rational power if there is a sequence of dominant rational maps over K, so that the source xn, the things at the very top, is actually rational over the ground field K, and the generic fiber is geometrically rational and irreducible over the function field. So a function field of the previous stage, of course, it's a non-closed field. So we want this to be geometrically rational, but we don't require rationality in this state. Okay, and then, of course, since we dominated by rational variety, so it's, of course, a unilateral variety at the bottom. So X is unilateral a posteriori. So then we can follow to that one sense. You can also demand, okay, maybe we can make the genetic fibers not just geometrically rational variety. Maybe we can get away with using forces under the restored. And we will call such a power a toric power. And then, well, the conjecture, we think about unilateral variety, maybe every unilateral variety admits such a rational power. Now, as always, there are some obstructions, of course, to rationality to unilateral varieties. Brower groups of abstract homology, and then, of course, if you pass up the chain, that would mean that these things are killed, all those classes are killed at the top. Now, you want evidence. Well, here, of course, all unverified homology upstairs is trivial. And what's the evidence? Well, let's start with eliminating one class. So we start with one particular non-trivial alpha and one HI and one phi. Well, then it turns out that the Volkata conjecture proved by Grabowski implies that you can indeed fill that class, in fact, any finite set of such classes, on such a power, where the generic fibers are forms of projected space, Browns-Severi. So it suffices to use Browns-Severi control. Now, one of the issues, it doesn't prove our projection. For the following reason, first of all, new unverified classes can show up. You fill one class on the descent variety, splitting variety, suddenly there's another class coming out of the blue. And the second component of that, or more important perhaps, is that in these constructions, there is no information about the rationality of both classes. Yeah, that's splitting variety. We have no idea. You may have filled all the classes in the process, but upstairs, you don't know what kind of variety you have. Now, so what we do, though, in our paper is that we prove the existence of a toric rational power for these universal spaces, V of G, where G is, well, special group, but that class of special groups includes all the groups that show up in our theory of universal spaces for unverified homology. So, well, in some sense, of course, it still doesn't prove our conjecture, because just because you have it for unverified homology coming from these universal spaces, it doesn't mean that so why overlap you can do the same thing for, let's say, even for one class of the original variety. Okay, so I hope I've sort of motivated enough. So the Noether's problem, as I mentioned, has a negative solution. V mod G need not be rational. And then, well, you can ask, well, can you rescue Noether's problem in some form? And our conjecture, and modified Noether's problem would be, don't look for representations of the kind of G, don't look for linear actions, simply look for actions on rational variety. They're not nonlinear. And then we hope that for any finite group G, there will be a rational G variety with a generically clear action, so that the quotient is rational. Now, what's the evidence? Well, so this is the work of this problem, and the evidence is the theorem that if you have this special group, and as I said, the special groups, they capture all unmodified homology or override. And so you can look at these kind of special groups, X mod G. In particular, there are plenty of examples where X mod G is not rational, but it belongs to the Brown group and so on. Then we need to prove that there is for such groups G some rational variety X, not only linear action, non-linear action, because the quotients are rational. All right, so this is sort of maybe all these connections are not completely straightforward the first time you see it, but so here we have a class of non-linear groups G. We know that they're universal, and that all unmodified homology classes will be captured on quotients of representations of such things, and for those we produce our rational powers, and you know, for those we also produce these rational x's with quotients rational. Okay, and there are plenty of examples like that of such G, so that the obvious action, the linear action, produces non-stable rational quotients. So I hope that the discussion explains our interest in computations of unramified Brauer groups of these fields of invariance for representations, but also for even nonlinear actions, arbitrary varieties, let's say rational varieties with G actions. All right, so you know, some group cohomology. So G is a finite group, M a G module, and in applications, it's going to be the Picard group of a variety, a projective variety, and we'll consider group cohomology with coefficients in M, in particular with coefficients in K star, K is our ground field, and then I'll omit these coefficients with trivial G action. So here is a small table computing with group cohomology in the simplest cases when the group is cyclic. So H2, H3, or let's say a group is Zn plus Zm, then you get very explicit sinks, and this is well known to, of course, people doing group theory, group cohomology, and so on. Okay, now G is an arbitrary finite group, and you can look at the set of bicyclic subgroups. So these are abelian subgroups with two generators. Could be cyclic, but not more than two generators. And Bogomolov proved the following very general result, that the unramified Brauer group of a quotient of a field of invariance for any action are simply all the classes in the Brauer group, so that the induced class alpha A and the Brauer group of a different field of invariance, namely Brauer of K of X invariance under A, where A is one of his bicyclic subgroups, is unramified. So this is sort of a very general characterization of the Brauer group of the fields of invariance. And in particular, if you look at representations of G, if you look at an abelian group and you look at the representation, then over an algebraically closed field, as I said, V mod A is rational. And for a rational variety, the unramified Bragg group is trivial. So if you want to compute the unramified Bragg group of representation modulo G, then, and that's the general theorem of Bogomolov, it's very simple. It's expressed in terms of completely discrete things. It's the kernel of H2 of G, with coefficients and K star, to the sum over all the bicyclic groups, H2 of A. It's the kernel of that. And he calls that group B0 of G, and this is a Bogomolov multiplier group. And of course, this being such a straightforward definition, attracted attention of people doing explicit things. There is a lot of follow-up work computing with B0 of G. There are, for example, groups of order P to the 5 or P to the prime, like 3 to the 5 or 2 to the 6, with non-vanishing B0 of G, and again, many, many papers. And there is also a general result that if you look at things like Sn or An, almost simple groups, then with a very few explicit exceptions, maybe like 5 exceptions or something, B0 of G is 0. So, and so once you have that in place, you'd like to understand other G actions, in particular toric varieties. Well, how do you get the action of a finite group on a toric variety? Well, if I have the characters of the forms, or to three times the G model, and then you simply look at the representations of the G, so homomorphisms of G into G, L, and G, where it's dimension of the torus. And that will get to an action of the characters of the torus, and that will induce a G action on some representation of toric variety. And in such a situation, there is also a formula that looks very, very similar to what I showed you in the other case. You look at M, which is that lattice of characters with a G action. You add Q mod Z with trivial action, and then you simply compute the kernel for this homomorphism. And again, the bicyclic groups play a distinguished role here. So we've just posted with Andrew Crash in January a paper where we computed in many more cases. Strangely, even PN was not known. So Bogomolov looked at the case representation, linear action, and if you look at the projected linear action, an action of PN, you will not know. Well, then we started pushing some more, so maybe all of this minus. And then we did the flex variety example. And then, of course, well, why not do it in full generality? And so we did serious sort of an example of generality. Now, the key step, given that first result of Bogomolov that I mentioned, is to understand the unramified problem of quotients by abelian groups, abelian subgroups of G. And it turns out that even for PN, if you look at the quotient of one PN by the abelian group, it's unknown. It's rational. And certainly not for this minus of Flegler. So while we don't know that result for PN, we did prove that the unramified Bragg group of such quotients by abelian groups is rational. Sorry, it's trivial, and that helped us to produce a general formula, in those cases mentioned. I mean, certainly, some of these cases might be accessible, to rationality proofs, but I don't know. And so our general algorithm to compute explicitly the unramified Bragg group of the field of invariance for any, including nonlinear actions of G, for any rational G variety, works like this. So what we compute first is actually the Bragg group of the quotient stack. Next, there is something in stack theory called de-stackification. It's some stacking procedure. lots of substacks, but also taking some respect construction. The bottom line is that you can produce what the model, where the core modalized space is Q. In general, of course, we look at the core context of G, so I have a singular sort of representation spaces and so on. And then to find the unmodified problem in the field of invariance, you have to perform some residue computations on on this nice model, and in particular extract an unmodified Brownian quotient from the Brownian quotient stack. So those are the main steps. And so again, a priori, we're looking at a completely classical problem, which is a Brownian field of invariance, but that stacky thing, to be very helpful with this passage effects and group actions to invariance. So how are these things connected? So we look at the map from the quotient stack to BG, and then we write down the Fourier spectral sequence. And what we see is, we have the characters of G injecting into XP the group of isonormal classes of generalized line bundles on X. And of course, you can change the linearization by character. Then you map to classes in the Picard, sorry, it's in the X, the Picard that are invariant on G. Then you map to H2G. Then you map to the Brownian of the quotient stack. And then you see in red, I call it out H1G Picard. And then there's the map to H3, and then the second one and so on. And the group H1 GPCAR, well, that plays sort of an important role in the study of G axis of variety. Now, the first thing to note is that the moment you have a fixed point for the G action, the basic propriety will tell you that delta 2 and delta 3 are 0. And that cuts off certain pieces away. And so now that we're kind of looking at G actions and each one of the car, I should tell you a little bit about the basic questions in the equivariant geometry, dynamic geometry. You want to understand whether some action on a rational variety is equivariant birational to action of projective space. Then these are representation of G. And this is an honest linear action. Or stably linearizable if it comes to after you multiply this projective space in trivial action, and I spoke about related problems in previous meetings here in Miami. And one of the obstructions to stable rationality is a non-vanishing of this H1 GP car for some subgroup in your group. But there are other obstructions to stable linearizability, and that is the non-vanishing of the image of delta 2. It's known as the n absolute. Or non-vanishing of the image of delta 3. So these are the kind of abstractions, oops, that, okay, there is no, all right, so let's look at this in the simplest case, namely rational surface. So at least we know that the quotient by a finite group is going to be rational. Every unirational surface is rational. Closed field. And, well, Bogomolov and Prokhorov computed that H1 GP car for actions of cyclic groups, Z mod P, where P is a prime. And all you need to know is there a curve of genus at least one in the fixed locus? If there is one, it is unique. And the H1 GP car is going to be Z mod P to the 2G, where G is the genus of that curve. And this uses the classification, Delpezzo surfaces, conic bundles, and things like this, equivariant minimal model problem. And Schindler generalized this to actions of other cyclic groups, but again, under the assumption that the stabilizers are maximal. So there are no intermediate cases. So, all right, so let's take our favorite surface, a cubic surface. Here is an equation. And consider Z mod 2 respect to the Z mod 3 action on it. And the Z mod 2 action is you switch the sign on Z.
And the Z mod 3 action you multiply with the third root of unity at W, and clearly equation is preserved. And well, in the first case, you have a curve of genus 1 when you put Z equals 0. And in the second case, you have another curve of genus 1. It's W equals 0. And so correspondingly, by Bogomolov-Prokhorov, if you have the Z mod 2 action on this PCAR, you get Z mod 2 squared, and Z mod 3 squared. Okay, so let's continue with cyclic groups. So for cyclic groups, acting on rational varieties, you always have a fixed point. So in particular, delta 2 and delta 3 are always 0. But the table I showed you that actually H2 GK star is also 0. So for cyclic groups, what we're seeing is that with H1 GK star, which is of interest to us, is exactly the broad group of the quotient stack. You could look at this both ways. You can either find ways to compute H1 GK star and then what the broad group of the quotient stack is, or you can go the other way. So that's what we have. And so how do we compute that broad group of the quotient stack here? Well, the first thing to notice is that, of course, when you restrict to the generic point of the quotient stack, well, that's just the field of invariance. And so the broad group of the quotient stack, well, it's going to be a subgroup of the broad group of the field of invariance. And because in our case, we have a rational variety, so it's just the broad group of the function field of P2, just huge. Then there is this exact sequence, the broad group of the functional field of a surface maps to H1 overall curves, C of K with torsion coefficients. Then you can keep going to all points on the surface. And the basic result is that the broad group of the quotient stack, in fact, injects into a sum of each one of those curves where the inertia is non-trivial. What's said here is that it's sort of eliminated by the order of inertia. So if the order of inertia is 1, it's a curve. If not, does not have generic stabilizer, then you don't see it at all in the computation of the broad group of the quotient stack. And so immediately you have this action, the cyclic group acting on the surface, you find some curves which have non-trivial stabilizer, and those are the only ones that you need to. Okay, that's of course on reduction. And then there is actually a characterization. So you do this on a model of a surface. It's a standard form. There is some open U, so that the boundary is sort of very nice. And nice means that the G orbit of every component of the boundary is a smooth divisor. So we only look on that model, of course, with non-trivial generic stabilizer. And then there is a description. You look at the collection of these classes in H1, and then it comes from a class in the broad group of the quotient stack, if and only if the local ramification indices work out somehow for that other map. And so, of course, kind of impossible to, I guess, immediately sort of see what it's doing without examples. So let's look at the Bogomolov-Prokhorov and Schindler result. Well, so we have sort of a unique curve in here with a non-trivial stabilizer, and we compute that each one, and that gives us exactly the Z mod P to the 2G that we're supposed to see. But then we can also look at other cases. So in particular, the next slide, I'll give you an example for a cyclic group with sort of varying stabilizers. But for non-cyclic groups, like abelian groups, non-abelian groups, you get sort of an interplay between delta 2, delta 3, this, that, and the other. And in our paper, we have examples showing that you can have an example with delta 2 non-zero, delta 3 non-zero, and you just see how that homology moves between the different terms in that basic long exact sequence that I wrote down. Now, the paper that we just posted in January does it in all dimensions. And it's much, much harder, as you can imagine, the computation and much, much more involved. So let's look at that cubic surface that we saw before and the Z-mode 6 action on it. We have, of course, we see that the square of the generator, we see the Z-mode 3, the third column is the Z-mode 2, exactly the cases that we looked at before. So if you look at these things individually, you solve this homology. But it turns out that in this case, there isn't. So actually, it's a standard form of each of those genus 1 curves fixed by the diameter of the 2, diameter of the 3, there is an induced residual action, which also has fixed points. So the quotients are P1s. And so previously, we were getting those unmodified classes from simply unmodified classes from the height of these curves, but now they're gone. And so 2 torsion and 3 torsion classes, if you have sort of stabilizer of the 2, then it's for the 2 torsion class, stabilizer of the 3 torsion class, you sum them together. The only way they connect to 0 is level 0. So the brow group of the stack here is actually trivial. So Z-mode 6, the full action gives you trivial each one, but every subgroup gives you an open each one. Okay. So now let's return to again G actions, stacks, and fields of invariance. Maxim Kontsevich and I introduced these Burnside groups, free abelian groups on birational equivalence classes of algebraic varieties. So it's whatever equivalence classes of function fields of varieties of dimension n over k, and we prove specialization for these group specialization. So you look at the family, you look at the generic point, look at the special fibers, and then there is sort of a specialization of homomorphism in this context. And there are many geometric applications that I discussed here, previous conferences. Then we can, of course, look at varieties together with G actions, and in particular actions of abelian groups. And there was a paper of Maxim, Pleston, and myself several years ago. It's a group on tuples of n tuples of characters up to permutation and some relations. You take the quotient, and it turns out that that thing, which we call Bn of G, captures G equivariant birational invariance, which means that if you have an action of an abelian group on X, you write down the class of the action in that group, and that's a well-defined birational invariant. And what's the class? Well, it's a sum of these kind of symbols over all strata, the reducible components of the fixed locus of the group. And in each stratum, you record the weights in the tangent bundle of the action. And so, well, here, again, you only look at maximal stabilizers, the full group. And Andrew Crash and I introduced for arbitrary finite G, what we call the G Burnside group, where we now look at symbols which encode not only the weights in the normal bundle to some stratum with a non-trivial stabilizer. So you record the stabilizer, you record the residual V action on the stratum. It's a subgroup of the centralizer of the stabilizer. And then you record the weights in the normal bundle, and then you have to introduce relations, some pretty complicated relations. And what we introduce captures the rational invariance of such actions. And so the class is computed on a standard model where all the stabilizers are abelian. And we prove specialization in this context as well. But so it was sort of a very general result. There's no geometric applications, but in fact, I posted a paper yesterday on the archive, that is already on the archive as of yesterday, where we have first geometric applications for singular cubic threefolds of this formalism, that you can look at some actions, you don't see any abstractions in the generic fiber, you specialize, you find abstractions, and therefore the very general fiber is not linearizable. And so, of course, you're motivated then to look at Burnside groups for stacks. Well, what would that be? Well, if we deal in a group on birational Phillips classes of stacks, so of course, it's fine stabilized with different Manford stacks. And we did define something like this by generators and relations. And then you compute the class the way we were computing the class in presence of G actions. Namely, you look at all loci on your stack where you have kind of a non-trivial generic stabilizer. It's a stabilizer stratification. You compute this on an appropriate model where all the stabilizers are abelian. And beta is against sort of the representation. And well, we show that whatever we define on symbols and relations is actually a birational invariant for stacks. And then we were asking, well, how does it compare to the previous things? We show that indeed there are natural homomorphisms from Burnside groups varieties as G actions with Burn and G to this Burnside group for stacks. And what you do is you take the G action and you just map it to the class of the quotient stack X mod G. And then we want a specialization. And it turned out that specialization is actually not working in this context. And that has to do with something that maybe was not as apparent in people doing birational geometry of stacks, because how do we think about birational geometry? So you can think about birational means you only care about the risky open subset. But you see the risky open subset just a function of the field of invariance. And you're sort of obliterating all the structure. So, well, that's not the notion of birationality. A good notion of birationality was model the equalization approach. You say that two stacks are birational if there is a diagram, up and down, blowing up in the subset, something like that. Well, that's the notion. And what's kind of interesting, there is the stack structure, it's one here, you know, there are 100 pages on birationality of birational. And there's nothing on birationality of stacks. It's not surprising, it would be an important notion. So, well, what we realized was that there is no specialization here, and in fact, the really like fundamental issues. You look at the quasi-projective stack. How do you compactify? What's a good way to compactify such a state? How do you keep track of a stabilizer specification? So in any event, so the outcome is that while there is no such thing for the full Burnside group of stacks, there is actually a modification that does work. And the key difference or key important ingredients is when we write down these symbols, some of the stabilizer stratification over all the substacks, we have, of course, to identify up to birationality all the substacks. But now that identification, again, up to which birationality? And so if you, in that formula that I showed you, in that stabilizer stratification, if you introduce additional relations by weakening the notion of birationality, mainly declaring that each term state if prime of birational is a function field is the same, then you get a compatible formula. And then that further quotient of the Burnside group of stacks, which you call Burn bar, that has specialization. So to summarize, maybe I'll finish a couple of minutes earlier. We've discussed connections between equivariant birational geometry and classical invariant theory, Newton's problem, computation of various invariants, and particularly the unramified Brouwer group, and the role of quotient stacks in these computations. All right, thank you so much.